Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. My name is Mr. Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Right, today we are going to be looking at the fundamental counting principle. We are going to be building up from the concepts that we showed you the previous week when we were doing basic probability principles. So we are going to take it from there and then look at the concepts that govern counting principles, right? By the end of this lesson, you should be able to understand the origin of the fundamental counting principle. You should understand the factorial notation as one of the most important notations to be used in the fundamental counting principle. You should be able to use the fundamental counting principle to arrange objects without repetition. You should be able to use the principle to work with sitting arrangements, book arrangements, and word arrangements. You should be able to use the fundamental counting principle as well to work with digit numbers as well as the codes. You should be able to use the fundamental counting principle to arrange identical objects. Remember, also should be able to use the principle to work with probability related problems, where now you use counting principle to calculate the probability of a certain event occurring. That's very important as well. Right. Obviously, they continue here to say use the fundamental counting principle to count the rest of the objects if counting of objects, or if we're in the situation where counting becomes a bit tedious or difficult. Apply the counting principle to solve probability-related problems, as I just indicated. We can obviously look at the CAPS document on page 49, as well as the exam guideline that was published in 2021. Check on page 7. It gives clarity to the scope within which you should be operating on as far as the fundamental counting principle is concerned. Right. Obviously, you never go into any math lesson without having prior knowledge that can be useful in that particular lesson. For this particular lesson, the prior knowledge that you need would be the probability terminology, compound events, complementary events, mutually exclusive events and inclusive events, independent events, and exhaustive events. Should be able to also use your probability equation and those probability identities. Right, let's now begin with the background of the fundamental counting principle. We are going to take you back to where you began with your counting when you were still at preschool or at elementary primary school there. Mathematics began with counting. Initially, we're using fingers to count 1, 2, 3, and so on. Then later we used our cold drink lids to can count and add items. These things were used to help with counting, but these are only practical for small numbers. What happens when large number of items is to be counted? This chapter focuses on the use of mathematical techniques to count different assortments of items. Right, introduction now. Let's look at the introductory work on this. When dealing with occurrence of one or more event, that event is referred to as the compound event. It is important to determine the total number of outcomes of a compound event, i.e. it helps us to get the size of the sample space. In an attempt to count how many outcomes of a compound event are possible, we can use a tree diagram, or we can use a table, or we can list all the possible outcomes and count them. Now, let's check here. Our goal is to count the total number of possible outcomes of a compound event. We want to determine how many outcomes are there not what the actual outcomes are. That's very important. In the counting principle, we want to just know how many they are, not what they actually are, those outcomes, just how many they are. So now, suppose that you have 3 t-shirts and 2 trousers. How many different outfits can you wear? Now, if you want to use a tree diagram here, we are having 3 options of wearing t-shirts. That can be shirt 1, shirt 2, or shirt 3. We have 2 options of wearing trousers. That can be trouser 1 or trouser 2. Now we're interested in the total number of outfits that we can wear. So we're interested in the total number of outcomes here. Now let's check here how we can actually come up with a tree diagram. You can see here, these are the options for what? For the t-shirts. These are the options. This represents now the options. Options for the trousers. Because we have 2 trousers. So it can be trouser 1 or trouser 2. Now let's look at the options for the t-shirts. We have now 3 options. These are the options. Options here. Options for the t-shirts. These are the options for the t-shirts. Now, if you are to draw a tree diagram for this, you can see that now you can wear t-shirt 1 with trouser 1. That's the first outcome. Or you can wear t-shirt 1 with trouser 2. That's the second outcome. So we have 1, 2. Or you can wear t-shirt 1 with trouser 3. That would be the third option here, third outfit. Or you can wear t-shirt 2 with, or rather you can wear what you call now trouser 2 with shirt 1. That would be the fourth option. You can wear trouser 2 with shirt 2. It should be shirt 2 here. That would be the fifth option. You can wear trouser 2. That would be trouser 2 there. Trouser 2 with shirt 2. That can be the sixth option there. If you are to count all these options, you can see that you have a total number of 6 possible outfits that you can wear. You can see there it's 6 possible outfits that you can wear. So now let me go back here. It's 6 possible outfits. Remember, we are interested in the number of outcomes, not what the actual outcomes are. But fortunately here, we've also been presented with what the actual outcomes are. But we know that they should be 6 because we physically counted them. Right. Now, if we look at the number of outfits, now how would we look at the number of outfits if you were given 5 t-shirts and 200 trousers? What if now we are saying we have 500 t-shirts and 200 trousers? You see here it was easier and more practical to can draw a tree diagram because we know that we have 2 options for the trousers, we have 3 options for the t-shirt. So it became easy for us to can draw our tree diagram. Now let's check here. If you are given 500 t-shirts and 200 trousers, now it becomes very difficult to can draw a tree diagram. It is not a practical tool to can use here. So it would not be practical to use a tree diagram. And then for this reason, we introduce now the fundamental counting principle. So the fundamental counting principle is going to assist us to be able to count the total number of outcomes if the tree diagram can no longer work or the tree diagram will no longer be practical. So we need to generate a way to be able to count outcomes without having to use the tree diagram. Now, the fundamental counting principle is a rule that is used to calculate the total number of outcomes in a situation. Now, that is the rule. We call it the rule of product. It says, the fundamental counting principle states that if there are m ways of doing task 1 and n ways of doing task 2, then there are m times n ways of doing both tasks. If there are m ways of doing task 1 and n ways of doing task 2, then to do both of the tasks combined, you have m times n ways. So you multiply the two that you have there. You multiply the two ways for m and the ways for n. So you say that there are m times n ways of doing both tasks. Remember, this can be extended to more than two tasks. If you have A ways of doing task 1, B ways of doing task 2, C ways of doing task 3, and so on, then you're going to have that to do both or all the tasks combined, you would have A times B times C, and so on. Right, so that is the rule of product there. Now let's look at example 1. Let's revisit example 1. Remember, in example 1 we had 3 t-shirts and 2 trousers. So we have, let's go on there and see, we have 2 trousers, and we have 3 t-shirts. So if we call this one M and this one N, we can see there are 2 ways of doing task M and there are 3 ways of doing task N. To do both of them combined, so the total number of outfits shall be given by what? M times N, which would be 2 times 3, which gives us 6 outfits. 6 possible outfits like that. It's 6 possible outfits. If you check from the previous slide here, we got 6 possible outfits by making use of the tree diagram. But here we get 6 possible outfits by making use of the fundamental counting principle, which means we can also be able to calculate for what? For 500 t-shirts, we'll know that M is equals to 500 and N is equals to 200. To get the total outfits, then this would be M times N. That would be 500 times what? Times 200. Then you'll be able to get the answer there. So that is the basic counting principle. That's the basic application of the counting principle. If you have M ways of doing task 1 and N ways of doing task 2, to do both of them combined, you'll have M times N ways. Remember, the fundamental counting principle is concerned with the number of options that you have of executing a specific task. You are not actually interested in performing the task, but you are interested in the options that are available of performing that particular task. So that's very, very important. Now, let's move on. Obviously, here we are bringing back the total outfits. If you have 500 t-shirts and you have 200 trousers, then that takes us to 100,000. So that's what I was actually calculating there. Right. Now let us look at an example, another example that would want us to actually do our basic application there. At a school's fundraising event, each person who wishes to buy a meal may choose only one food item from each of the following 3 tables. So you can see it's table 1 and table 2 as well as table 3. But a person can only choose what? Only one food item. Now, what I like about this example is that now it is going to show us the difference between the fundamental counting principle when we use the options and also making a particular choice. The choices that are available to us and making a particular choice. Now let's check. Only one food item for from each of the following tables, which means at the end, when a person has a plate, the person has dished up, the person would have one item here, one item there, one item there. So in that plate, there will only be 3 items. In one specific plate, there will only be 3 items. But that's not what the fundamental counting principle is concerned with. With the fundamental counting principle, we are concerned with the options that you have of having to do what? Of having to make a specific choice. We are aware that in table 1, you'll make one choice. In table 2, you'll make one choice. In table 3, you'll make one choice. Ultimately, at the end, you would have made 3 choices, which means that your plate would have 3 food items. But remember, the counting principle is not concerned with making a specific choice, but it is concerned with the number of options that you have of making that choice. Now, let's check here. We have, let's say table 1 is M, table 2 is N, table 3 is O. So which means that the total number of how many different meal combination, total total meals here should be given by what? Should be given by M times N times what? Times O. Because we have M ways of choosing from table 1, N ways of choosing from table 2, O ways of choosing from table 3. Now let's check here. From table 1, 1, 2, 3, you have how many? You have 3 options or choices. Table 2, you have salad, baked potato, chips, or rice. You have 4 options to choose from. Although you'll choose 1, but the number of choices that you have are 4. So, table 3, you have 2 options. It's either ice cream or fruit salad. So now, we would have that this would be given by 3 times 4 times 2. So this would be 12 times 2. That would be 24 different meal combinations. So 24 different meal combinations. So that is what you'll have there. 24 different meal combinations. So that's how you should be approaching it. You see here, I did actually put up the solution there to say we have table 1, we have table 2, we have table 3. In table 1, there are 3 options. Table 2, 4 options. Table 3, 3 options. Now, fundamental counting principle says you should multiply the options together. So you can see there the total meal combinations is 3 times 4 times 2. That would give us 24 different meal combinations like that. Right, so now let's see. What did we do here? We looked at the number of options of performing each task, and then we said can multiply those options to get 24 meal combinations. It does not mean in one plate there will be 24 food items. No, there will be 3 food items, but we are looking at the choices that you have of having to choose a specific food item. Right, now there's an activity. There's an activity for you to do. So I think in about 4 minutes, you should be able to do and complete this activity for basic application. You have 4 minutes to do the activity, and your 4 minutes time starts now. Right, hello and welcome back. I hope that you were able to work with this problem. I hope that you did not encounter any difficulties. Right, let's check it together here. A party pack of 3 items can be made by selecting one item from each of the following choices. Choice 1, we have Smarties, Astros, Jelly Tots, or wine gums. And then choice 2, Coke, Fanta, Sprite, ginger beer, cream soda. Choice 3, we have donut, Chelsea pan, or cheese roll. Now, how many different party packs can be made? If we are to refer to this one as M, N, and O there. M, how many options do we have for M? 1, 2, 3, 4. We have 4 different options for M. And then for N, we have 1, 2, 3, 4, 5. We have 5 different options for N. And for O, we have 1, 2, 3. We have 3 different options for O. So now, total packs will then be given by what? We are looking at what? M times N times O. So this would be 4 times 5 times 3. 4 times 5, that is 20 times 3. That should be 60. 60 packs. So we have 60 packs. Let's confirm that one. 4 times 5 times 3. That is 60 packs. Like that. So now, that is the first one because we have 4 options here. We have 5 options there. We have 3 options there. That was M, N, and O. Right. And then now they say if a party pack must contain Smarties, you see now we are starting to have what we call now a restriction to say a party pack must contain Smarties. How many different party packs can be made? Which means that for let's see, for choice 1 here, you should have Smarties. So we are not interested in any other item in choice 1. So you should have just Smarties. So we should make sure now that the total packs would be, remember, it is M times N times O. But the number of options for M has now been reduced. Why? Because they said must contain what? Smarties. So which means that the other items here, you don't care about them. You want Smarties for choice 1. So how many Smarties do we have there? We have there 1 option for M because there's 1 Smartie there. So multiply by the number of options for N are still 5. The number of options for O are still 3. So you can see that now the total packs will then be 15 packs like that. It will be 15 packs like that. You see, if you are making a definite choice for one of these, then you are actually bringing in now what we call a restriction because you restrict choice 1 to only Smarties. So if that happens, you can see the number of packs have reduced from what? From 60 to 15. So that is where now you can be asked to calculate what? The probability. If someone says, determine the probability that a party pack contains Smarties. Determine the probability that a party pack must contain what? Smarties. Then you will need to work with number of elements in that event, divide by the number of elements in the sample space, where the sample space has no restriction, but the number of elements in the event is what? Containing Smarties like that. So that's what we have there for B. Right, we move on. We are going to get into these application with probability related problems a bit later. We will get to that. Right, introducing factorials. Now, we have products here that we want to try to congest, and we must learn mathematical ways of being able to do that. And we use what we call the factorial notation here. This, good people, is not an exclamation mark. It is only an exclamation mark when you do language. In mathematics, Using that symbol means you are using what you call now a factorial. So a factorial is denoted by that mathematical symbol. To thoroughly comprehend the use of factorials, let us consider the following example. Now let's look at this example. How many ways can two learners sit in two chairs? So we have two chairs, we have two learners. So for the first chair, there are two options. Because learner 1 has equal chances of sitting in chair 1. Now that learner 1 has sat in chair 1, for chair 2, there's only one option because there were two learners. So that would be 2 times 1 like that. Now let's check. 3 learners in 3 chairs. 1, 2, 3. Chair 1, chair 2, chair 3. The number of options for chair 1, because you still have 3 learners, it means that any 3 of them can sit in chair 1. So you have 3 options. But now for chair 2, now that one of the learners is on chair 1, we are left with now 2 learners, 2 options. For chair 3, 1 option. We can multiply those. Now, what about if it's 4 learners? 2, 3, 4. For chair 1, we have 4 options. Chair 2, 3 options. Chair 3, 2 options. Chair 4, 1 option. So if we multiply those, we get 4 times 3 times 2 times 1. What about if it's 8 learners and 8 chairs? 1, 2, 3, 4, 5, 6, 7, 8. Just like here, chair 1, chair 2, chair 3, and chair 4. Here it would be chair 1, chair 2, chair 3, chair 4, chair 5, chair 6, chair 7, and chair 8. So now what we do is, for the first chair, because there are 8 learners, there are 8 options, because any of these learners can sit in the first chair. Now that one learner, remember in chair 1, only one learner can sit, but we have 8 options of occupying that chair because any of those learners has equal chances. Now that one learner is on chair 1, for chair 2 there will be 7 because one less learner now should be considered because that learner is sitting on chair 1. Chair 3, we have a learner in chair 1 and a learner in chair 2. So we are left with 6 learners. So there are 6 options because any of them can sit here. And so on. 5, 4, 3, 2, and 1. And then the fundamental counting principle says you need to multiply those options because we are using what we call the rule of product. Now, if you look at all these, congestion or all these answers here, they start from a specific number and they end with 1. If you check, the first one starts with 2 and decreases to 1 and then it stops. The second one starts from 3, decreases to 1 and then it stops. So it's 3, 2, and 1. So it decreases by 1 until what? Until the lowest value, which is 1. Check the third one. It starts from 4, 3, 2, 1. So these products are decreasing by 1 until they get to the number 1. 8 learners, same thing. Starts from 8, decreases by 1 until the number 1. Now, if they said now 100 learners in 100 chairs, you see the product was going to be 100, 99, 98, and so on. So now we must find a way because you can see that these products get bigger and bigger. So for much bigger numbers, it will not be practical to write down these products as descending digits there until the number 1. So for that specific reason, we introduce what we call what? A factorial. So a factorial, you will take the highest value of that particular product, 2, and then to represent the rest, you use now what? Factorial. So this 2 factorial represents 2 times 1. Here, because you have 3 times 2 times 1, you take the highest, which is 3. To represent the 2 and the 1, we use what? The factorial. So that factorial then here in this context represents 2 times 1. If you have 4, because it decreases from 4, 3, 2, and 1, you take the highest number, which is 4, and then to represent 3, 2, and 1, we use what? We use now a factorial. So you can see we are writing this as one value that is representative of the whole product. So for 8 here, you're going to take the highest value, which is 8, and then to represent 7 times 6 times 5 times 4 times 3 times 2 times 1, we use what? A factorial, like that. So that is how we are going to use our factorials. And our factorials are going to be very, very useful here in counting principle because we work with a lot of products like that. So this is how I've actually tried to represent it. From the above examples, we notice that the number of options decrease successively by 1 until we reach the number 1. We therefore use this idea to introduce factorials. As I've explained before, 8, the factorial will then represent this part. This part is now represented by what? A factorial. 4, this part is now represented by what? A factorial. 3, this part 2 and 1 is now represented by a factorial. 2, this part 1 now is now represented by what? A factorial. So that is how we congest, which means that if we have n factorial, if we have n factorial, we should have n times you subtract 1, n minus 1, times you continue subtracting 1, n minus 2, and so on up until you get to 3 times 2 times 1. That is what the factorial means. And most importantly, we define 0 factorial as 1. This would be the definition. This would be the definition of what? Of a factorial. Definition of a factorial. By definition, 0 factorial is equals to 1. Excellent. So now factorials would be playing a very huge role when it comes to the arrangement of objects. Now let's go on. Arrangement of objects without repetition. First rule number 2, remember rule 1 was the fundamental counting principle. Rule 2 says if we arrange n things in n ways, then we can do that in n factorial ways. Just like we were doing there, 3 learners, 3 chairs, 3 factorial, right? Can go back here, 2 learners, 2 chairs, 2 factorial. 3 learners, 3 chairs, 3 factorial. 4 learners, 4 chairs, 4 factorial. 8 learners, 8 chairs, 8 factorial. So we are saying if the number of objects that you want to arrange are equal to the number of placements that are available, so they can be arranged in what? In n factorial ways. Like for an example here, it says, how many ways can we arrange 4 different books in a shelf? So if you have that shelf, the total number of ways you can do that should be what? 4 factorial. Should be 4 factorial. But if you are going to take it step by step using the fundamental counting principle, we are going to then have to check, okay, we have 4 books and we have a shelf that can accommodate all the books. So we present the first space, the second space, the third space, and the fourth space in a shelf. The number of options for the first space are 4 because any of these 4 books can sit in space 1. Yes, there will be 1 book there. Only 1 book will sit in that space, but we have 4 options because any of those books has equal chances of being there. Space 2, now that 1 book has occupied space 1. In space 2, we have 1 less book, 3 options, and so on up until we get to space 4, where there will be 4 options. By using the fundamental counting principle, we'll multiply the options in the different spaces. So we get that is 4 times 3 times 2 times 1. That is 4 factorial, as I indicated, which is equals to 24 ways, Good. Now, let's move on. Arrangement of objects without repetition. Now, suppose that now we want to know you have 5 learners to be seated in 3 chairs. You see now the number of chairs are now less than the number of learners. So in order for them to sit, you'll have chair 1, chair 2, and chair 3. So 5 options for the first chair, 4 options for the second chair, 3 options for the third chair. You can see now that this number does not decrease to 1 because the number of chairs available are less than the number of learners available. So for that, we can use what? We can use the permutation rule, which is written there, which is defined as n factorial over n minus r factorial, or n permute what? R, where R represents the number of spaces that you have and n represents the total number of objects that you want to place into those spaces. So now, if we have 9 different books, how many ways can we arrange 4 of them? You see, you have 9 books, you want to arrange 4. Remember, if it was 9, arrange 9, it was going to be 9 factorial because it's n number of objects, n number of spaces, n factorial. But now it's n books, but now we want to arrange 4 of them, so it's n permute 4, or it would be n factorial over n minus r factorial. That would be 9 factorial divided by 9 minus 4 factorial. Now, we have 9 different books we want to arrange 4. We can take it basic, 3, 4. Using the basic application, we want to arrange only 4 of them, so we can open the 4 spaces, and then from there we can say, okay, we have 9 options here, 8 options there, 7 options here, 6 options there. If you multiply these two, then you're going to get the solution for that. Now, let's check here the solutions as they come in. You see, space 1, space 2, space 3, space 4. In space 1, we have 9 options because all of these 9 books have equal chances of sitting there. In space 2, we have 8 options because one book has already been occupied, or rather has already occupied space 1. Similarly, for space 3, there would be 7, as well as space 4, there would be 6. Now, the total ways, you can see it's 8 times 7 times 9 times 8 times 7 times 6. One can also say this is the same as what? As 9 what? Permute what? Permute 4. Which is the same as what? 9 factorial divided by 9 minus 4 factorial. Now let's just check whether this product will be the same as what you get here. So we have 9 factorial, which is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, divide by 9 minus 4, that is 5 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. So you can see here from 5 until 1 is the same as that. So this and that will take each other out. You are left with 9 times 8 times 7 times what? Times 6. And this answer here is the same as what we have there. So that just shows that using the permutation and actually placing those objects will give you the same answer. But it is much better if you place those objects there rather than using that permutation rule. But obviously you get to the same results, right? Now, application to probability. Sometimes in counting principles, you'd be required, remember this is a section under probability. Sometimes in counting principle, you'll be required to perform calculations for what? For probabilities. So in that case, we will then be required to clearly identify the sample space and an event guided by the question. So you must have a sample space where a sample space represents what? Possibilities without restriction. The sample space will represent possibilities without restriction, and the event will be clearly defined by the question. Clearly defined by what? By the question. So here, unlike in grade 11 probability, where the sample space is always given, here sometimes you will have to calculate the sample space. And in doing that, you need to then isolate the sample space, isolate the event, calculate both of them, marry the two to determine probability. Right, we move on. Arrangement of objects with constraints or with restrictions. Sometimes they give you restrictions that you have to abide by. So in case when you are given restrictions, we should be looking at the following guidelines. If objects are grouped together, we treat those objects as a single item. Very, very important. That can be moved within an arrangement. That's key. If they're saying these objects must move together, you treat them as a single object that can be moved within an arrangement. But remember, within that single object, there can be also further arrangements. Now, if the position of the object is specified, if we are told that the object is in a specific position, you need to fix that object in that position and then arrange the rest of the objects. If the objects are grouped and the position of the group is specified, we fix that group in that position, and remember that within the group there can be further arrangements, right? Now let's see the application of these 3 points that I gave you. Oh, before that, let's look at arranging the rest. Now, this is also key. Sometimes what you have to count is practically not possible, or it can be tedious to count what you actually want or what the question demands, and becomes much easier to count by difference, which means that you should be able to say, for an example, if I have 5 possibilities in total and I have out of these 5 possibilities, there are those that meet a condition and there are those that do not meet a condition. If I know that maybe 2 of them do not meet a condition and someone wants me to calculate the number of those possibilities that meet a condition, I can take the total, which is 5, and subtract the 2 that do not meet a condition. The remaining 3 like that would be those that are meeting a condition. So we are counting by difference. We said 5 minus 2. So sometimes you can be required to say you have, for an example, if you have a 4-digit code, 4-digit code taken from the sample 1, 2, 3, 4, 5. And then they say to you, what are the total number of codes where you use at least one 3, where you've used at least 1 3. For a 4-digit code, remember, if you use at least 1 3, it means you can use a single 3 or more. So you can use 3 in this position. You can use 3 in this position. You can use 3 in this position. You can use 3 in that position. That is if you used 1 3. There are 4 different options that I can start calculating with. However, at least 1 means you can use more. You can use 2 3s in this position. You can use 2 3s in this position. 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 You see, there are many. You can also use 3 3s. 3 3s in this position. 3 3s in this position. You see, you can still use 4 3s because they said at least 1. So if you check the options that you have, there are too many. So it will become very difficult to count using what? At least 1 3. For that reason, we are going to be arranging by difference. So we say arranging the rest. So which means we are going to take all possibilities. For this case of these codes, we are going to take total number of possibilities without restriction. If you've used all the codes without restriction, subtract the total number of possibilities of not meeting a condition. We can say here, what if we take out 3? And we say let's count all possibilities without a 3. Then we are going to say from the total, we subtract those that are without a 3. We are definitely sure that those that remain are those that contain at least 1 3. So that is why we go and revert to what? To arranging the rest, or what we call the NOT rule, like that. So I am going to move on. You are going to see it in application. Arrangement of objects with constraints or restrictions. Now I have an example. I've given you the background by giving you these three useful guidelines. And then from there, I also gave you a further background by checking what? Arrangement of the rest of the objects. Now, let's look at a practical example where this can be done. 3 boys, Sipho, Mandla, Clive, and 2 girls, Bongiwe and Ritumezi, are to be seated next to each other in 5 different seats to take a group photo. In how many ways can the 3 boys and 2 girls sit in a row if they sit in any order? Now, sitting in any order, you have how many? You have 5 individuals, 5 individuals, or we can say that 5 learners. And then if they can take a group picture, it's also in 5 what? In 5 spaces. So this should be n and n, that should be n factorial, which would be 5 factorial. But now if we do that, we see that it is given by what? 5 factorial. Why are we saying 5 factorial? Because we have 5 spaces. There are 5 options here of space 1, 4 options space 2, 3 options space 3, 2 options space 4, and 1 option space 5. So if you multiply these, you can say it's 5 factorial, which is 120 ways. Now, in how many ways can they sit in a row if Sipho and Bongiwe must sit together? You see now, what are we doing here? We are saying Sipho and Bongiwe must sit together. If Sipho and Bongiwe sit together like this, if this is Sipho and Bongiwe, if they sit together, then it means that they are moving as an item. So you are going to treat them as what? As one object. And then from there, how many learners will you be left with? It's 3. 3 remain. So now, how many objects do you have in total to arrange? It's the one object which comes from a group of, which comes from what? Grouping Sipho and Bongiwe. And then from there, we are left with the 3 other learners. So how many? We have 4 objects to arrange. Because we have 4 objects to arrange, how many ways can we arrange them? 4 options for the first position, 3 options for the second position, 2 options for the third, 1 option for the fourth. So to arrange them, it would be 4 factorial. So this 4 factorial here is for what? Is for the total objects. It's for the total objects. That is 4 factorial. However, between Sipho and Bongiwe, they can sit like this, starting with Sipho and then Bongiwe, or starting with Bongiwe and then Sipho, which means that because they are 2, 1, 2, there are 2 options for the first position and 1 option for the second position, which means they can also be arranged in what? 2 factorial ways. That's where this 2 factorial is coming from. So this 2 factorial is coming from the fact that Sipho and Bongiwe can change positions. So you have two tasks to do. Task 1 is to arrange the 4 objects, which is 3 remaining plus 1 group, which you treated as a single object. And then task 2 is to arrange within those objects that were treated as a single object, there are also further arrangements. So this would give us 48 ways. Now the next one, in how many ways can they sit in a row if Sipho and Bongiwe refuse to sit together? You see, now we are bringing in another problem. If they refuse to sit together, you have how many? 5 learners. It means there should be Sipho Bongiwe. There should at least be Sipho Bongiwe. There should at least be one space between them. So you can see that you can present a lot of possibilities there. You can present a lot of possibilities where you have to count them one by one, and it becomes a bit tedious to do so. So as a result, we are going to revert to what? To counting them by difference. So we are going to say, since we want them not to sit together, we're going to take all possibilities without restriction. That would be 5 factorial minus the number of possibilities where they are sitting together. Then we'll know the remaining possibilities will be where they are not sitting together. Let's see here. So you see, we are going to take now all possibilities. The 5 factorial is for all possibilities without restriction. And then what about the 4 factorial times the 2 factorial? That would represent what? What we just calculated here. Possibilities where Sipho sits next to Bongiwe. So once we calculate the possibilities where they are actually sitting next to each other, we subtract from the total. Then the remaining would be when they are not seated next to each other. So that's how you were supposed to approach that one. Right, I have an activity for you, and this activity in 2 minutes time, you should be done, or 3 minutes. Let's take it for 3 minutes. 3 minutes time, you should be done. And your 3 minutes time starts now. Right, hello and welcome back. Let's now look into this particular problem. Three boys, Sipho, Mandla, and Clive, and two girls, Bongiwe and Ritumesi, are to be seated next to each other in 5 different seats to take a group photo. So it's the same as the one that I previously worked on the previous slide. It's the same as this one, but I've added a few questions. So now, in how many ways can they sit in a row if the boys sit together as a group and the girls sit together as a group? Now, if you are to put boys as a group, you would have boy 1, boy 2, and boy 3. Because they sit as a group, you treat them as a single object, one object. And then from there, we also have girls as a group, girl 1 and girl 2. So you also treat them as what? One object. So in total, you'd have 1 plus 1, which is 2 objects to arrange. So to arrange these objects, you will have to do it in what? In 2 factorial ways, because it's 2 objects. However, the boys can interchange position. Because it's 3 boys, they can interchange position. 3, 2, 1. They can do that in what? 3 times 2 times 1 in 3 factorial ways times. The girls also can interchange positions, and they can do that in 2 factorial ways. So that's what you are looking at there. Let's see. So the total arrangement would be 2 times 3 factorial times 2 factorial. We explained that the 2 factorial is for all objects, and then the 3 factorial is for boys changing positions, and the 2 factorial is for girls changing positions, like that. So that's what we get there. Now, the next one says, calculate the probability that the boys and the girls are to alternate. Remember here, we need the event, number of elements in the event. We need number of elements in the sample space. In the sample space, we've already calculated the number of elements. In the first question, we got 5 factorial. We've already calculated it in the first question. In the event, what is the event? Girls and boys are to alternate. So how do they alternate? Boy, girl, boy, girl, boy. Let's check if we start with a girl. Girl, boy, boy. So this will not work because it's not now. It alternates for the first 2, but now the last one, instead of being a girl, it's a boy. So we are going to be looking at this one now. Let's check here. There's only one way this can happen. It's boy, girl, boy. Let's check. Remember, this is boy position, boy 1, boy 1 position, boy 2, as well as what? Boy 3, because they alternate. So this one would be girl, this one would be girl. So there are 3 options of having the first boy to sit there because there are 3 boys. 2 options of having the boy to occupy the next boy position. 1 option of having the boy to occupy the last boy position. For the girl position, 2 options. First, because there are 2 girls, and then 1 option last. So that is the total number of ways there. Which means now, if we want to take it further, the number of elements in the event, I've already explained that it's 12, which is that's what we got here is 12, and in the sample space it's 120. So the probability of an event E occurring would be 12 divided by 120, which would be 1 out of 10 chances. So that's how you were supposed to actually approach that one. Right, let's move on. Arrangement of objects with constraints or restrictions. We move on. We have letters of the word lovers are used to form different arrangements without repeating the letters. How many letter arrangements are possible if the first letter must be an L and the last letter must be an S? So we have 1, 2, 3, 4, 5, 6. 4, 5, 6. The first letter must be an L and the last letter must be an S. So you have actually fixed You have actually fixed those letters there, which means that you are left with 4 letters to arrange. So 4 remain, because those ones have been fixed there. So you can do that in 4 factorial ways, because there are 4 letters there. Let's see. So we get that the total should be 4 factorial ways, because already you fixed a L in the first position and fixed S in the last position. Why are you doing that? It's because you are told that it must start with an L and end with an S. So now, how many arrangements are possible if the first letter must be a vowel? It's still 1, 2, 3, 4, 5, 6. Now, for the first letter to be a vowel, let's check the vowels that are available. It's O and E. So it's O and E. So you are going to fix a vowel. You have 2 options of doing that, because there are 2 vowels that are available. And then you have now the 5 remaining letters, or rather the 6 remaining letters, because 1 letter has been placed or fixed in the first position. You fixed 1, but you had 2 options of doing that. So this should be 2 times what? 6 factorial. Let's see. Or it's 2 times 5. Let me see. 1, 2, 3, 4, 5, 6. It should be 2 times 5 factorial, because 1, 2, 3, 4, 5 remain. You've used 1 in the first position, and then you have 5 factorial for the remaining ones. Right, let's go to the third one. How many arrangements are possible if L, V, and R must be grouped together in any order? So we have L, V, R. If they are grouped together, you treat them as what? One object. And then from there, how many letters remain? 1, 2, 3. 3 remain. Now the total will then be what? 4 objects. You have 4 objects to arrange. Because it's 4 objects, they can be arranged in 4 factorial ways. So that is where the 4 factorial is coming from. It is coming from what? All the objects there. But remember, letters L, V, and R can also interchange position. You can start with L, V, and then R. You can start with V, L, R. You can start with R, V, L. You can make any arrangements here, because these letters can also interchange. But because there are 3 letters, there are 3 options here, there are 2 options there, there's 1 option that those letters can actually change position. So that would be 3 factorial ways. So the 3 factorial is L, V, R can what? Can change positions. They can change positions like that. Right, we move on. There's an activity I am going to actually, by looking at time, I will skip this activity so that we can cover more concepts like that. Let's look at arrangement of identical objects. Arrangement of identical objects. Now, if we consider the word dead, if letters of the word are arranged, then we can get 3 different arrangements: dead, add, or DDA. If we want to arrange these letters, it's 3. You can see that it's 3 ways that we can do it. Now, however, if repeated letters are different, suppose that the repeated letters, the D's, are different. So we have D1 and D2. You can see that the number of arrangements now increased to what? 1, 2, 3, 4, 5, 6. We have now 6 ways in which we can arrange these letters. So there are 6 different letter arrangements of if identical letters are treated as different. So if they are treated as different, we use D1 and D2 just to differentiate them. So you can see that the number of ways now increase if letters are treated as what? As different letters. Now, we want to know, if you check in the above example, it was only practical to count, to say we have 6 ways, because we can physically write down those arrangements. But once we start having a big word like Mississippi, then it becomes difficult for us to write it down as individual arrangements that we can actually count at the end. So for that, we will formulate a rule that will allow us to be able to arrange letters if we have much longer weights. So now, in order to do that, we are going to say the number of the arrangement of n objects. It will be n factorial. Divide by p are identical, it will be p factorial. Remember, these are what? Identical. If you have identical letters, p factorial. Different letters, q identical, q factorial. So this is q identical, identical. And then if we have r identical, it will be r factorial and so on. So this is also identical, r identical. So those that are identical, you'll divide by those so that we can avoid counting the same letters twice. Now, what is important to consider here is that if you have arrangement of identical objects, an examiner is not compelled into telling you that repeated letters are treated as what? Are treated as identical objects because, or as identical letters. Because if you look at this word here, you can see that the eyes are the same. So the examiner is not compelled into telling you that they are the same. But if the examiner wants you to treat them as different, then the examiner is compelled to telling you that treat the repeated letters as different. Now, let's see, consider the word needed. How many different arrangements can we make if we consider the E's and the two D's as different letters? If they are different, it would be E1, E2, D1, D2. So it would be 1, 2, 3, 4, 5, 6, 6 factorial. Shall be 6 factorial because those letters are different. Now, but check if these two, the E's are not 2, they are 3. Sorry for that. There are 3. So if these letters are different, if they are identical, then you see that it will be 6 factorial divided by 3 factorial. What is this 3 factorial for? It's for the E's, because there are 3 E's, so we divide by 3 factorial. What is this 2 factorial for? This 2 factorial is for what? The D's, because they are 2 D's, like that. So now, let's see. The arrangement must start and end with the same letter. So here, if it must start and end with the same letter, case 1, you can have it start and end with what? With E, because if it starts and ends with the same letter, you'll consider the letters that are repeated. And then what would be your case 2? Case 2, you can start and end with what? With D, like that. So now, if we look at the options there, case 1, start and end with E. If you start and end with E, it means that you are going to have 1, 2, 3, 4, 5, 6. It's 6. 1, 2, 3, 4, 5, 6. You start and you end with E. You are left with what? 4 letters. So you are left with 1, 2, 3, 4 letters. So you'll arrange them in 4 factorial ways. But remember, if you started and ended with E, you still have D's that are repeating. So it will be divided by 2 factorial for what? For the D's, like that. So if you start and end with E, then you'll have 4 factorial divided by 2 factorial, like that. Now, if you start and end with D, 1, 2, 3, 4, 5, 6, you start and you end with D, you are left with 1, 2, 3, and 4. So this would be 4 factorial for the 4 letters that remain. But you have 3 E's. In those 4 letters, you have 3 E's. So you're going to divide by 3 factorial, and this 3 factorial is for the E's. So that's what you have there. Case 2, start and end with a D. So you see we have 4 factorial divided by 3 factorial. That gives us 4 arrangements. So to get the total arrangement, we will take word arrangement 1 plus word arrangement 2, which is 12 plus 4, which gives us 16 arrangements. That will give us 16 arrangements, like that. Now, activity, obviously, because of time, we're not going to be able to do that as well. Let's see, maybe we will come back to it. Let's see digit codes. That would be the last concept That would be the last concept for the day. That would be digit codes or numbers. Now, when we look at digit codes or numbers, it is important to know the difference between the two. A number cannot start with a 0. It's very important. We've seen questions before in past exam papers where they do not specify. They just tell you it's a digit number. And if there was a 0 there, you should make sure that as a natural restriction, 0 cannot occupy the first position, which means 012 is a 2-digit number. However, a code can start with a 0, which means 012 is a 3-digit code. Right. Moving on, let's look at the examples that we can actually look at when it comes to codes. Let's look at those examples there. How many 2-digit numbers can be formed if repetition is allowed? You are given the digits 1 to 8. So how many digits? 1, 2, 3, 4, 5, 6, 7, 8. So the number of elements in the sample space, we have 8 numbers there. We write this as 8 numbers. We are interested in making a digit number. Remember, number cannot start with 0. A number cannot start with 0. Fortunately, in our sample space, we do not have a 0. So we have an advantage there. But if there was a 0, then the number was not supposed to start with a 0. Now, how many 2-digit numbers can be formed if repetition is allowed? We want 2-digit numbers, and repetition is allowed. So what does that mean? It means that you're going to check now how many options for the first position should be 8. Remember, if there was a 0, we were not going to start with a 0 in the first position because a digit number cannot start with a 0. So we would have 8 options for the first position. And then from there, because the digit can be repeated, for the second position, we'll also have what? We'll also have 8 because you can still use the digit that was used in the first position. So now you can see here, if we bring along those solutions, there's 8 times 8, which is 64 numbers that we can form. Now let's look at the second one. How many 4-digit numbers can be formed if repetition is not allowed? 4-digit, 1, 2, 3, 4. And repetition is not allowed. For the first position, we have 8 options because any of the 8 numbers can occupy the first position. Now, second position, let's check. Since repetition is not allowed, we've used 1 number in the first position. So which means that now we have 1 less number from the total, which was 8. So we have 7 options here. For the third position, 6 options. Fourth position, 5 options. Then we multiply them together. Now let's see the solution as it comes up. Of course, 8 times 7 times 6 times 5, which gives us 64 numbers. And then the next one says how many 4-digit numbers between what? 4,000 and 5,000. Now this starts to be a bit tricky now because they are saying between what? 4,000 and 5,000. Now let us examine the range. And they say repetition is allowed. Let us examine the range of these codes. These codes, they said between 4,000 and 5,000, which means the lowest code can be 4. It starts with 4, 4111. Remember, between 4,000 and 5,000, it's a number that are greater than 4,000, but less than what? Less than 5,000. Which means the biggest number that we can form here can be 4, right? Remember, greater than 4,000 and less than 5,000. That is what 4,000 and 5,000 means. It means that the number must be greater than what? 4,000, but less than what? 5,000. That's what it means. And remember, numbers that are less than 5,000 are numbers that start with 4. So we have that this would be 4,888. That should be the highest number because 8 is the highest digit that we can have in our sample space, and 1 is the lowest that we can have. So that's why we say our range can start from 4,111 to what? To 4,888. Now let's check, which means that the number must start with what? a 4. So it's a 4-digit code, which means that the first value here, by all means necessary, must be a 4, because the lowest starts with a 4 and the highest starts with a 4 for the numbers that are between 4,000 and 5,000. So there's only one option there of using a 4, because there was one 4 in our original sample that was given there. Now, the repetition is allowed, which means that here you can use any of the numbers, including the 4. So you have 8 options here, 8 options there, and 8 options there. Which means that now, because repetition is allowed, starting from this position, you can use any of the numbers. Repetition is allowed, any of the numbers. Repetition is allowed, any of the 8 numbers. So let's bring up the solution like that here. Let's see. I have my pen here is a bit flat. So for that reason, let's just see whether I can be able to continue. If not, it's back now. So let's see. The options are not coming through. It means that I'm a bit stuck. It's a technical error. Let's just take 1 minute for us to can rectify that technical error and come back quickly and wrap up. Right, welcome back. Let us wrap up our lesson. Apparently here my pen was actually low on battery. However, we continue. Now, the third one here, obviously I have worked it out with you here to say it would be 1 times 8 times 8 times 8, which gives us 512 different numbers there. So it was important that we were able to actually look at the range of the available codes, and that range then assisted us to know that the first position here we have only 1 digit, which is the number 4. So that's very, very important. When these problems become a bit difficult, then sometimes you'll need to consider the range, right? Obviously, this one was yours, but because of time, you cannot be able to work through that. Now, let's look at the summary of everything that we've done. We looked at the fact that counting principle is concerned with the number of options or possibilities of doing a specific task. And then we looked at the factorial notation and as a way that we can mathematically congest much bigger products to smaller products that we can actually manage when performing specific fundamental counting principle problems. When objects are grouped together, we said, please consider those objects as a single object that can be moved within an arrangement. When objects within an arrangement, or when the position of the object within an arrangement is specified, we fix that object in that specific position and arrange the remaining objects. Right? When dealing with codes, we should always remember that a digit number cannot start with a 0, but a digit code can start with a 0. When dealing with arrangements of books or letters, please check whether the books or letters are identical or different. Remember, if they are identical, then we'll use the n factorial divided by what? P factorial times Q factorial times R factorial and so on. That is if they are identical, so that we can remove the count twice so that we cannot count the other objects twice, because the rules that are used are different. Because if they were different, if they were identical, we use this. But if they were different, this would be when they are identical. If they were different, we're going to just use n factorial. If they were different, we're just going to consider that as n factorial. So we should be very, very careful of that. Right, thank you very much for tuning in. The next time we meet you would be when we prepare for a prelim exam. That would be the final preparation, revision for paper 1. We hope that by then you will be ready. We'll just be here to brush up a few concepts with us. Thank you very much. Please take care of yourselves and take care of each other and practice mathematics. Bye-bye.